Hello, guys. We are moving on over to the second part of our populations lecture. Today we're going to be chatting about K and R selected species, as well as survivorship curves. And this is stuff that, again, I think is super interesting. If you don't, that's okay. But this is the kind of thing that people that I'm friends with in real life get really tired of hearing me talk about, because this is stuff I bring up all the time. I think it's very interesting. K-selected species, we're just kind of picking up where we left off yesterday. So if you remember, we closed out yesterday with the different factors that change population abundance and distribution. So the things that affect where you can find populations, and the things that affect how abundant populations are, right? So that's where we closed out yesterday. Today we're picking up with K-selected species. So K-selected species and R-selected species are very different, and we're going to explain why. So K-selected species, they're going to live right below the carrying capacity, and the environment that they're living in is going to be pretty stable, pretty predictable, I guess stable is the best way to put that. I want to make sure I'm on the right page in the notes as well. If you're following along in our student notes, we are on page 6, where it says reproductive strategies and survivorship curves. So with K-selected species, they're not going to have a lot of offspring. And their offspring and the species in general is going to have a long lifespan. These populations are generally really constant and competitive. So populations stay pretty level. It takes a long time for them to reach maturity. They reproduce later in life when they're older. They're protected by parents and potentially by whole groups of adults of that species. So if you look at your notes on this part, it goes into a little bit more detail. Let me make sure it's not about to go there here. No. So your notes on page 6 go into a little bit more detail. And it talks about intrinsic growth rates and their abundance and carrying capacity. Carrying capacity, that definition can be found. I know it's in here. I'm pausing myself. So I'm not seeing it in the notes, which is frustrating to me, because carrying capacity is definitely a term that we need to be familiar with in this unit. So something to keep in mind is that carrying capacity is just, and it's self-explanatory as well, but it's just the number of any individual species that any specific environment can support. So if there's a limiting factor of some sort, if there's only a certain amount of food, if there's only a certain amount of water or space, then once the population, if we're talking about elephants, once they've reached that carrying capacity, they're not going to be able to keep adding members to the population without older ones dying off, because the environment won't be able to sustain more organisms with the resources that it has available. Hopefully that makes sense. So picking up where I left off, that threw me off for a second, because carrying capacity should be in here. Make sure we're familiar with that. It might come up later down the line again. Substantial parental care. So basically, K and R selected species, it's kind of like the strategy of either have very few offspring and spend a lot of time raising them, making sure that they know how to exist as adults, stay with their parents for a long time, and then go off and succeed as an adult of that species, or R selected species. Very creepy crawly spider picture. Sorry if that upsets you. I did not make this slideshow. Like I said, it's from College Ready, A+ College Ready. So our selected species are kind of the opposite in a lot of ways. They might be in more unpredictable environments or unstable, things like the ocean or insects and things like that. They have the ability to disperse offspring widely, so they can have lots and lots and lots and lots of children. They have tons of offspring. Usually the offspring are very small. They have little or no parental care. So the parents do not spend time raising the babies. Massive deaths of offspring. This is kind of like the shotgun effect, right? They're like, I will have 1,000 babies and then maybe like 10 of them will survive, right? So just a different strategy, you know? They have a short generation time, so their lifespan isn't quite as long. And they have a high fecundity rate, just meaning that they can produce tons of offspring. They have a high fertility rate. So when we compare these two, right, you've got K-selected, meaning that organisms are, like humans, are K-selected, obviously. They have 1, 2, maybe 3 babies, and they raise them very carefully, and they teach them a lot, and they stay with them. They have strong parental instincts, like elephants, like primates, like humans, like giant pandas. They spend time raising the babies and teaching them how to exist. And then you've also got our selected species. With our selected species, I always think about Finding Nemo because our selected is like the opposite, right? They're like, well, we don't really want to raise the kids, but we'll just have like thousands of them, and then maybe some will survive, right? So when you think about Finding Nemo, Marlin and what was Nemo's mom's name? Please hold. Coral. His mother's name was Coral. So Marlin and Coral had hundreds of little babies, right? And then the only one that ended up surviving and with a birth defect at that was Nemo, right? Spoilers if you haven't seen Nemo, though. Like, come on. So something to think about. An easy way to remember that, maybe. Short generation time. They're just kind of assuming that a lot of the babies aren't going to live. They're like, well, a lot of them might not. But we had a lot, so maybe some will succeed. So that brings us into survivorship curves. Survivorship curves. You've got type 1, type 2, and type 3. And essentially what survivorship curves are showing you is what the lifespan of different types of organisms will look like. So they are going to be very different for K-selected species and R-selected species. So generally, sorry, I got distracted. Okay, generally, K-selected species are going to follow a type 1 or type 2 curve, and then R-selected species are going to follow a type 3 curve, which makes perfect sense, right? So basically what this means, you've got, I'm going to exit out of this so we can see both parts of the graph well here. So you've got age in relative units right here on this x-axis. And then on your y-axis, you've got number of survivors. So when you look at this, if you look at type 1, it's a convex curve, and it means that most individuals do live to adulthood. So they're living, not that many have died off over this first span. And then most mortality meaning deaths, occur during old age. So type 1 is going to be humans, deer, elephants, things that have a high survival rate early in life, and then generally as they get older, then they die like humans. Type 2 is generally just a straight line. An individual's chance of dying is completely independent of its age. So it's just as likely to die when it's elderly as when it's first born. So chance of dying and age are 2 independent factors there. Then type 3 is going to be a concave curve. This means that very few individuals are going to live to adulthood, and the older you get, the more likely it is that you'll die. So snapping turtles, redwood trees, and oysters are the examples that they give. Because when you think about it, in this case, we're looking at an acorn. How likely is it that an acorn's actually going to turn into a tree. Not super likely, right? It has to be just the right scenario for that to happen. So definitely something to think about with that one. So it looks like right here is what I was looking for earlier. No population can grow indefinitely. Obviously, that makes sense, right? That statement makes sense. There are a few reasons for that. You've got environmental resistance, all factors that act to limit the growth of a population. So anything that might limit the population, that could be resource availability, it could be human involvement, any of those things. You've got carrying capacity, which is what I was looking for earlier, which is the maximum population a given habitat can sustain. And then you've got intrinsic rate of growth. The intrinsic rate of growth is just the maximum potential for growth of a population under ideal conditions and unlimited resources, basically. So intrinsic rate of growth would be like absolute Goldilocks scenario. They've got everything they need. They've got plenty of space. They've got no predators, that sort of thing. So it's not a very realistic ideology there. So we're going to get into population calculations later on down the line. So for right now, we're sticking with these ones. I hope this was helpful. Email me if you need me. And that's that.